Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the comparison of numerical and experimental results for the compressible flows. So we'll just see some examples of, let's say, flow over airfoil and flow over a missile or flow over a rocket, or let's say flow over a car. So with high velocities, and how do we compare the results of numerical and experimental, and what are the key parameters involved to compare those results. So how do you scale down the models, and how do you compare the values of CL, CD, CM for everything what we do in experimental setup and what we do in numerical setup. We'll see it in detail. So in the previous session we have seen the low speed flows, or let's say incompressible flows. So for incompressible flows, we have seen the Reynolds number as the key factor, so which is rho v L by mu. So the Reynolds number is a key parameter which was used for comparing the experimental and numerical results for the incompressible flows. So we have taken some example, let's say flow over cylinder, so which we simulate for the numerical setup. Let's say this is a domain. So for the domain, so we have drawn a cylinder, so which is of let's say diameter d is equal to 10 meters. So let us assume, so it has a Reynolds number Re is equal to 3000. Okay, so this same thing we can do it for the wind tunnel also. So how? So we have taken a wind tunnel, so we have a convergent section, so we have a test section here, so we have a diffusion section here. So in the test section we will place the model. So again, if we are able to simulate the Reynolds number of 3000, and so the diameter here d is equal to, let's say, 1 meter. Okay, so d is equal to 1 meter, we have d is equal to 10 meter. So here how we are making the Reynolds number equal for the numerical and experimental, we will see here. So let's say, so Re of experimental E is equal to rho of experimental V of experimental. So reference length or diameter we can say of the experimental divided by so mu of experimental. Next, numerical Re of n, so which is of numerical, so rho of numerical, so velocity of numerical, so reference length of numerical, so divided by mu of numerical. So here if we compare, so to make the Re as 3000 and Rn as 3000, so we need to actually play with the density of the fluid medium, velocity and reference length. So basically once we have the density, the corresponding dynamic viscosity will be given. So we can also change the medium. So let's say we are doing experiment for flow over cylinder with air. So we can do with water for numerical, and we can still compare the result. Why? Because they are non-Newtonian fluids. So when you take non-Newtonian fluids, they are Newtonian fluids. So when you take the Newtonian fluids, so we can actually compare the Reynolds number of experimental and Reynolds number of numerical. So let's say here what do we have? So we have diameter d is equal to 1 meter and we have diameter d is equal to 10 meters. So first similarity theorem rule is the shape should be same and the size doesn't matter actually. So if you want to compare the values of let's say CL, CD, CM and other force coefficient values of two geometries with the same shape of different sizes, their Reynolds number should be equal. So let's say what we have, so in the numerical we are using let's say water, okay, and in the experimental we are using it for air. So what we do, so basically, so density of R, let's say rho E, so we will take it as air 1.225. So if we take the reference velocity VE and the reference length LE, so divided by the dynamic viscosity of air. Similarly, you have the water. So density of water is 1000 kg per meter cube, and so the reference velocity of numerical, and this one, so and this one. So what we do is we will change the velocity, and since the reference diameter here it is 1 meter and here it is 10 meters. So the major thing is we will play with the reference length and we will play with the reference velocity, so that it will be equal to Reynolds number of 3000. So whatever we do, so we have to compare the results of that particular geometry for the same Reynolds number. You cannot compare the Reynolds number. Let's say here if you are using RE 4000 and here you are using same 3000, you cannot compare those results of RE 4000 with RE 3000. So the major very important thing to compare the numerical results with the experimental setup is the Reynolds number should be equal, first thing, and the second thing is the shape of the geometry should be same. Size doesn't matter, but shape should be same. So if you are using Newtonian fluids, so you can use anything, air or water, so to compare or to do experiment. So this is one thing, so which we have seen for the incompressible flow, so where the Reynolds number is playing a key role or a key thing, so to equate the experimental and the numerical. So for compressible flows, so basically when do we say the flow is compressible? So let's say we have a parameter called Mach number M, so which is called V by A. So V is nothing but so the velocity of the object, or let's say velocity of the flow. So that can be anything. So that can be velocity of the body or the air. So you can take anything. So to the speed of sound. Okay. So in that medium. So let's say if you are seeing or if you are evaluating this Mach number for medium as air, the speed of sound in air we have to see. And if you are evaluating that Mach number in water, so what is the value of speed of sound in water you have to see. And if you are seeing in other medium, so whatever the medium you are evaluating, so in that medium, so you need to evaluate the speed of sound, and similarly the speed of the object in which medium is traveling. Okay, so what do we have here is like the Mach number will actually tell us so whether the flow is incompressible and compressible. So in general, so people researchers have identified that if flow speed is crossing approximately greater than so 110 meter per second, so the flow is getting compressed. Okay, so this has come from the experimental justifications. So less than let's say 110 meter per second, so we have the flow as incompressible. So we have two very important categories, which is of compressible, other one is incompressible. So for incompressible flow, so what we do is like we use the Reynolds number as the key parameter, so to compare the results of different shapes for the numerical and experimental. Whereas for the compressible flow, so we need to use both the Reynolds number and the Mach number. Okay, so we need to see the variation of the Reynolds number and we need to see the variation of the Mach number. So these things are very important. Now, so let's say here we had spoke in terms of velocity. So let us see in terms of Mach number. So if Mach number is less than 0.3, so approximately, so this will be incompressible flow. Okay, so if Mach number is greater than 0.3, so this will go in compressible flow. Okay, so we have two categories, which is of incompressible and compressible flow. Even compressible flow has different domains. So where we say it as a subsonic flow, so we say supersonic flow, so we say hypersonic flow. Okay, so we'll see that thing. Okay, so when the Mach number is in between, so let's say 0.3 greater than number till 0.8. So we say the flow as subsonic. Okay, so 0 point in between 0.3 and 0.8 we say it as subsonic. So here we have a zone called transition, or let's say we have transition flow. Okay, so where if it is coming greater than 1.2, so we say it as supersonic. Okay, and we say Mach number is, and it should be less than 5. So if Mach number is greater than 5, we say it as hypersonic. Okay, so if Mach number is lying in between 0.8 and 1.2, so let's say 0.8 and 1.2, so here we have the combination of subsonic and supersonic. Okay, so you have the transition between the subsonic and the supersonic. So we'll see in detail for the flow or airfoil. So based on the Mach number, so we will adopt the CFD. So the CFD, so whatever we see, so we already seen in the previous sessions. So basic governing equations we use continuity, momentum, and energy. So when we have the flow as incompressible flow, so we will use continuity equation and momentum equation. So let's say if you have the flow like geometry as 2D, so we use continuity, and we use x momentum, and we use y momentum. Okay, so this is our thing. So if you don't have heat transfer, and if you have the flow as incompressible flow, we use continuity, x momentum, and y momentum. So for the same incompressible flow, so without any heat transfer, if it is 3D, so additionally you have z momentum equation. Okay, so additionally we have z momentum equation. Now if the this category we have already seen. Now when the flow is getting compressed, okay, so even though you don't have heat transfer, so what happens, the density changes. So if you see the moment continuity equation, let's say dou rho by dou t plus del dot rho v bar is equal to 0. So here what is happening, so this term, density term, changes with respect to both. So density term changes with respect to both the time and let's say space. Okay. So therefore, so we cannot neglect this term. Okay. So we have to perform that finite difference formulation. So whatever we have seen in the previous sessions. So let's say forward difference, backward difference, and central difference. So whatever the numerical scheme we see, so that thing we need to apply for this. So let's expand actually what happens. So dou rho by dou t plus, so here we can see dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w equal to 0. So this is the expanded form of continuity equation, so which is unsteady and compressible flow. Okay, so when the flow is steady, so this term will vanish. So when the flow is incompressible, also this term will vanish. Why? Because density will not change with respect to time. So when the flow is incompressible and flow is steady, what happens? This equation will be changed in this way. So rho of dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So in this way the equation will change. So this is what we have seen for the incompressible flow CFD. So when the flow is getting compressed, so we have to solve this full length equation, and we cannot neglect the density term as constant. So it also varies with respect to time, and it also varies with respect to space. So this is what we need to add for the compressible flow CFD. But basically in our course, majorly we'll deal with the incompressible flow CFD. So for the compressible flow CFD, so there are other special techniques which we will learn in further classes. Okay, so let's see basically what are the key parameters which we will have to equate for doing the compressible flow CFD. So here we have the Reynolds number and here we have Mach number. So we are doing experiment, let's say the flow over again the airfoil. So I think this airfoil is the cross section of the wing, so which is present in two categories. So one is symmetrical, other one is cambered airfoil. So the cambered airfoil is used for wing, symmetrical airfoil is used for the tail section of the aircraft. Okay, so now when you are performing the flow, let's say over the airfoil, so when flow is, it is in subsonic flow, so let's say the Mach number is 0.5. Okay, so everywhere the flow, so each and every section, so the flow will be subsonic. Okay, so you take every point, so you take this point, you take this point, you take this point, any point you take, so any point in the flow everywhere, see the flow will be subsonic. Okay, so now let's say it is crossing, let's say the flow is approaching nearly 0.7, something like that. So what is happening is, so when the flow is passing over the airfoil, it will expand. It will expand somewhere on the top. So why? Because on the bottom the velocity is low and pressure is high. So velocity is low. On the top, so pressure will be low, so velocity will be high. Okay, so according to Bernoulli, we know that as the pressure decreases, velocity increases. As the pressure increases, velocity decreases. Okay, so we have these things. Okay, so here what is happening on the top section, the pressure decreases and velocity increases. So since Mach number has V by A, so this velocity will keep on get increased such that it will approach a Mach number of 0.8. Okay, so now when it is again 0.8 and 0.9 and somewhere it will come 1.0. So when the Mach number is approaching as 1.0, so what happens? So when Mach number is equal to 1, so what happens? V by A is equal to 1. So therefore, so what happens? V is equal to A. So the speed of the object will be equal to speed of the sound. So at that instant, so all sound waves, so weak sound waves will form a wave by collecting all the weak waves together. Okay, so that is called a shock. Okay, so there is a small or a very thin layer, so which is a weak layer, so which is formed over the airfoil, so which is called a normal shock, so with a Mach number of 1. So here what is happening? So till this region the flow is subsonic. Okay, and after this region, or let's say this region, you have sonic. Okay, so here what is happening? At some point you have subsonic, at some point you have super, or let's say sonic, or let's say some supersonic. Okay, so at entire flow field it is a discontinuity. Okay, so it has some discontinuous. Therefore, so this sort of flow is called transonic flow. So the transonic flow is a flow where you have the combination of subsonic and the supersonic. So why? Because when you are increasing the Mach number, let's say here we have taken the first instant, so which is Mach number is equal to 0.5. So for Mach number is equal to 0.5, so what happened? So the flow field at every point, so it is subsonic. So you take bottom surface, you take top surface. So everywhere in the flow field, the flow is subsonic. Now here it is what is happening as we are increasing Mach number. Let's say it has gone to 0.6, 0.7, so 0.75, something like that. So the flow expands. On the top surface, the flow expands and it approaches a Mach number is equal to 1. So this approach is called the critical Mach number approach. So critical Mach number in the sense, so let's say we call it as free stream Mach number m infinity. Okay, so the Mach number m infinity at which there is a sonic Mach number formed on the body, so that sort of free stream Mach number is called MCR, critical Mach number. Okay, so at the critical Mach number, the flow changes on the airfoil or on the body such that it forms a sonic region. So this type of transition from subsonic to supersonic happens in between 0.8 and 1.2. So that's is called transonic flow. That is called transonic flow. So performing transonic flow CFD is a hectic task actually. So there you need to employ the numerical schemes of supersonic and numerical schemes of subsonic. Okay, so you have some difficulty of simulating. So people are doing research to investigate transonic flow in detail. Okay, so performing flow fully subsonic, performing flow fully supersonic is possible, but performing flow or let's say performing experiment fully subsonic, fully some place subsonic, some place supersonic is somewhat difficult task. Why? Because here load will be high, here load will be low, so you have oscillations, so you have the unsteadiness, so you have some zones subsonic, some zones supersonic, so at the you have sudden jumps, you have discontinuity, so these things will happen actually. Okay, so therefore what is happening, the shape of the airfoil itself has to be changed. Okay, why? Because let's say if you keep on going increasing the Mach number, let's say at Mach number is equal to some 1.2 or something like that. So what is happening, like for the airfoil, so there is a bow shock formed actually. Okay, so this is called bow, like bow and arrow. So this is a shock. So basically shock is a wave, so which is formed by collecting all the weak sound waves. So it's a thin wave, it's a very very thin wave. So across the shock there is a decrease in velocity actually and increase in pressure. Okay, so here we have decrease in velocity and increase in pressure. So what is happening, this shock wave is creating a drag called wave drag. Okay, so basically drag is a aerodynamic force which is reducing the velocity or the motion of the body, so depending on the medium here. So here when a shock wave is formed, so it is forming a wave drag which is pulling back. Okay, so it is reducing the body velocity such that so it is creating an additional impact on the body. Okay, so here we have this, and at the tail you have this edge. Okay, expansion wave. So here we have shock wave, here we have expansion wave, such that so pressure here, pressure P atmosphere and pressure P atmosphere is reached. Okay, so here the flow get compressed, here pressure increases such that here again at this region the flow expands, expansion wave forms such that pressure decreases and it will match with atmospheric pressure. So that's why, so what is happening, so we cannot use the airfoil shape geometry for the high subsonic regions, or let's say in the supersonic regions. So that's why people had invented, or people are starting using the delta wings. So where the shock wave get attached with the body such that so there is a normal shock and here you have oblique shock. So normal shock will reduce high amount of velocity or increase high amount of pressure over the body such that there is high amount of wave drag. So when you change the geometry from let's say the airfoil to the delta, so basically we say actually delta wing. So So you say diamond shaped airfoil, or we can say delta wing. So when we use in terms of this delta, so here you form oblique shock. So here we have expansion wave. So like here you have again the expansion wave, such that it will match with the exit pressure. Okay. So now what is happening here? So when you are increasing the Mach number, the shape is changing actually. So therefore the CFD also will change for the flow when you are changing the Mach number. Okay. So this region, we let us take it is of greater than 1.2 and less than 5. Now when the Mach number is increasing greater than 5, what happens actually? So what type of CFD we need to see? So when the Mach number is increasing greater than 5, so you have the molecular effects. So the bond between the molecules breaks. So the oxygen atoms and the nitrogen atoms, they break their bond. Why? Because I think we know the boundary layer. So boundary layer is a thin layer which is formed near to the wall. So outside the boundary layer, the flow is considered as inviscid, and inside the boundary layer we consider the flow as viscous. Okay. So this at this region, so we use viscous aerodynamics. So outside the boundary layer we use inviscid aerodynamics. Okay. So when you have the boundary layer which is attached to the body, so here when the shock interacts with the boundary layer, so that is called shock wave boundary layer interaction. So what is happening, the flow actually will generate a transition. It will generate some separations, or it will generate some eddies, such that you have unsteadiness. Okay. And when you keep on increasing, when you're keep on increasing Mach number, what is happening, so the shock will get attached to the body. It will come close, very close to the body, such that the heating of the body will take place. So the temperature limits of the material will increase, and whatever the air attached, or whatever the air that is trapped in between the shock and the body, will get heated up and it will get ionized. Okay. So and it will break in atoms. So therefore, so when we are having a Mach number greater than 5, so we need to see the CFD of the individual molecules. We cannot consider air only air for performing the simulation for hypersonic flow. So we have to consider whatever the molecules, so let's say oxygen atoms or nitrogen atoms or any other gases which are present at that altitude or during that phase. So we have to use those molecules. We cannot blindly take air. Why? Because, and one more thing, you cannot consider the air as a calorifically perfect gas. And the values of Cp, specific heat constant at constant pressure, and Cv and gamma, so these values will change with respect to temperature. So this actually Cp by Cv is equal to gamma. So basically we consider it as constant for incompressible flow, so where you don't have any temperature effects. So therefore Cp is constant and Cv is constant. So when you are increasing the Mach number, so when it is reaching supersonic, or let's say when it is reaching hypersonic, so the air becomes the thermally perfect gas. So basically the Cp and Cv, they will be actually depending on the temperature. Okay, they are not at all constant, and the gamma also is not constant. And one more thing, you cannot use simply air for the experiment, or let's say numerical simulation. Now, having this knowledge, so what is the key thing we have? So we have Mach number, so which is V by A, and we have Reynolds number, so which is rho V L by mu. Okay. So what we have to see, so when you are performing an experiment, so we have subsonic wind tunnels, we have supersonic wind tunnels, and we have even people are doing research for transonic wind tunnels also, and even we have the hypersonic tunnels actually. So where basically we call it as the shock tunnels. So in that you generate a blast of blast of flows between vacuum and the high pressure flows. Okay. So where you will actually influence, or like you will import the helium gases or other mode of gases, such that you will evaluate whatever the molecular effect that is coming on the body. So that is separate division of CFD and experimental setup. So we'll just deal with the supersonic flow, and we'll just deal with the subsonic flow. Okay, and we'll just deal with the incompressible flow. So the hypersonic flow division is separate. Okay, now when we see M is equal to V by A, R is equal to rho V by L, so we are performing experiment for airfoil. So what we need to do, so when you are doing, let's say, Mach number M is equal to 0.4, okay, and RE is equal to 2 into 10 power 6, okay. So this same thing, okay, has to be performed or used for both experimental and numerical. So let's say Mach number you have 0.4, you have Reynolds number 2 into 10 power 6. So if you use numerical as Mach number 0.4 and Reynolds number 2 into 10 power 6, same Mach number M experimental should be 0.4, same Reynolds number RE experimental should be 2 into 10 power 6. Okay, so here what is the key thing, what is the difference that we have seen? So in the incompressible flow, so only Reynolds number will be sufficient to compare the experimental and the numerical. Okay, so whether the size of the body is 100 meters, 1000 meters, 2000 meters, or 1 meter, so whatever it is you take, so irrespective of size but same shape, so only the Reynolds number is the key parameter, so which is used to compare the experimental results and the numerical results. But now, so what we have additionally Mach number actually. So we have seen, okay, what are the different regimes of Mach number and what is its importance actually. So as you increase the Mach number, you know, the Reynolds number independency will come, only Mach number dependency will come. Only Mach number dependency in the sense, for very very high speed flows or for very very high Mach numbers, only the only Mach number is sufficient to compare the experimental and the numerical things. Okay, so example is like we have seen the airfoil. So for the airfoil, let's say you have here as 1 meter, or let's say 1 meter chord length. Okay, so this one you do for experiment. Okay, let's say you have realistic airfoil, so which is of 10 meters. Okay, so this is of numerical. So in order to compare the results of experimental and numerical of the airfoil, same airfoil, so let's say you have NACA 2412. Okay, so we are taking the NACA series 2412. Same NACA series 2412 has to be considered, and the chord length, so it can be 1 meter, 10 meters, 100 meters, it doesn't matter actually to compare the results. So I told you again and emphasizing, the size does not matter, the shape of the geometry matters actually to compare the results. So whatever the series of airfoil used, if you use NACA 2412, same NACA 2412 airfoil has to be used, and we need to equate the Mach number and we need to equate the Reynolds number such that we compare the experimental results and we compare the numerical results of the geometry. Okay, so with this we conclude that the Mach number and Reynolds number will play a major role for the compressible flow. Only Reynolds number will play a major role in incompressible flow to compare the results of the numerical and the experimental models for the different geometries for different applications. You take rocket, or you take aircraft, you take car, Rolls-Royce car, or Audi, BMW. So any fast moving bodies, you take the missile also, so which is going on road, in air, or let's say in water. So anything you take, so you can perform experiment and you can perform numerical simulation. You can compare their results with the scaled down model or scaled up model based on the comparison of Reynolds number, based on the comparison of Mach number. Okay, so in the next session, we will see what are the numerical techniques that are used based on the Reynolds number using the momentum equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.